Hello everyone, you're welcome to this lecture. So we want to finish off with differential equations. We are on to our last chapter on nonlinear autonomous systems. I'll give an introduction and then we'll go on to the linearization theorem, or if you like, the approach of linearization, and then later on we'll look at Lyapunov functions and how you can use it to analyze nonlinear autonomous systems. Okay? So unlike the linear systems that we've looked at, like planar linear systems and so on, where you can actually compute an explicit solution, here it's very rare to have explicit solutions. All right? And so the mathematical machinery is not as well developed. There are few things available to us to be able to tackle such problems. And one of those techniques that we'll be using is called the linearization technique, under the linearization theorem. And then also, if you are able to get develop Lyapunov functions, then you could use that to analyze these nonlinear autonomous systems. Okay? And so we'll start off with the linearization theorem. This is like a background to it before we actually state the theorem. So we want to consider a two-dimensional nonlinear autonomous systems given by this. So this is the nonlinear, if you like, something like x squared minus y plus xy. This could be like y squared minus x or something. So f1 and f2 are nonlinear, okay, continuously differentiable. Now, if you let x star be given by this, right, x1 star, x2 star, let it be a fixed point, such that, well, once it's a fixed point or an equilibrium point, then if you put it into the right-hand side here, this should go to 0 and that should go to 0. So that's what we have here. All right. So in this case, we want to seek solutions around the fixed point. That is the idea of the linearization theorem. You want to look for solutions not in the whole plane, but you want solutions just around a neighborhood around the fixed point. That's all you can do for this this technique. So you pick a fixed point, which you are calling x star here, and then you expand or linearize about it. Okay, so you let x1 be equal to x1 star, which is your fixed point, plus a small perturbation, okay, xi1, and then x2 be equal to x2 star plus xi2. So this is just a number, right? This is a fixed point. This is a small, a small variable. Okay, xi1 and xi2. So once you have this, you plug these guys into the right-hand side of this equation and expand them. Okay. So that's what we're going to do. So if you plug, so f1 x will be equal to, we are expanding about x star. You're going to get f1 x star plus xi1, the derivative of f1 respect to x1 at the fixed point star. No, this is a vector. This is x1 star, x2 star, plus then you get xi2, the derivative of this with respect to x2 at the fixed point, plus higher order terms. These higher order terms constitute, things like they will have terms with xi1 times xi2, or xi1 squared or xi2 squared. All right, because xi1 is small, the square of that or the product of that is also very small, and so you can't neglect that. And because x star is a fixed point, right, f1 x star is of course equal to 0, and so you end up with this. Okay. Now, if you have forgotten how to do Taylor expansions in 2D, this is I've written something down here to help you out. So if I'm expanding the function f about x naught and y naught with delta x and delta y, so these are like my xi1 and xi2, and this is like x1 star, x2 star. If you expand it, this is what you get. All right. So these higher order terms are these guys, the squares of xi1, the product, the square of xi2. So these are very small. So this is directly that. Okay. You can do the same thing for f2. If you do that, you end up with this equation. All right. So we rewrite this 2 again. Now note note this. So we have expanded f1 to be this, f2 to be this. If you go back to the original equations, so you can plug them back in here, f1 and f2. Note that x1 dot, that's a derivative with respect to t, This is just a number, so x1 dot is the same as xi1 dot because this goes to 0 because it's just a number, right? It's constant. And then x2 dot is just zeta2 dot because this is also constant, so it vanishes. And so we plug f1 and f2 into the original equation and we get this system. All right? And so now this is a linear system because these derivatives are evaluated at this point, at this number. And so this is just a number. That is a number. This is a number. So these are now, you have converted the nonlinear system into a linear system by expanding using Taylor series. All right? And so these two systems you can rewrite as this. And this is more like the planar system that we have analyzed. Okay? And this A is referred to as the Jacobian matrix. It's a matrix consisting of the derivatives at a fixed point. And of course, zeta here is zeta 1 and zeta 2. Okay? So by doing a Taylor expansion, you have changed the nonlinear system into a linear system that we have machinery that we can analyze. Okay. So now this equation here, this linear system here is the linearization, okay, of the nonlinear system. Okay, so that's the linearized form of the nonlinear system. And so instead of analyzing the behavior of this nonlinear system, which is difficult to do because we don't have the solution, we don't have the machinery for it, we are now going to analyze the linearized form of it. Okay, but by doing that, we only know solutions around the fixed point, not the whole plane. Unlike the linear systems where we have a solution around the whole plane and we can play around, here we can only analyze closer to the fixed point. So that is the limitation, if you like, of this approach. Okay? Now, once we've linearized it, we want to know whether the behavior that we find around the fixed point is actually the true behavior of the nonlinear system. Okay, so that is what the linearization theorem does. It tells you whether after you have converted the nonlinear system to a linear form and you analyze it, does the behavior portray the right behavior qualitatively of the nonlinear system. Okay, so we'll state it. Before we state it, you can also extend this approach into a system with n dimensions. Okay, and the matrix, the Jacobian matrix, become this, just a bigger matrix. So it's the same thing. And so the linearization theorem states that if you have lambda 1 and lambda 2 as eigenvalues of the Jacobian matrix, all right, for if the real part of both eigenvalues are non-zero, and if the eigenvalues are not repeated, they are not the same, then you can conclude that the qualitative behavior of the nonlinear system will be the same as that of the linear system around the fixed point. Okay, that's all the linearization theorem says. So you notice that the theorem does not cover cases where you have purely imaginary eigenvalues. The eigenvalues, the real parts must be non-zero. Okay, so in fact, the theorem covers stable and unstable nodes, stable and unstable spiral points, and saddle and hyperbolic points. It doesn't cover centers where you have pure imaginary eigenvalues. Neither does it cover the case where you have repeated eigenvalues, that is improper nodes. Okay, so in the cases where it doesn't cover, the behavior could be the same as a nonlinear system, or it could be totally different. All right, and so that is basically what the linearization theorem does. Okay, so in the next lecture, I'll probably repeat some of these points, and then we'll go through an example to further increase our understanding in this. All right.